speaker is Leila Montasser from the Faculty of Medicine, Manufia University, and I'm excited to introduce Leila Montasser, who will be presenting modern technologies. Where are we living? So just a bit of background about Leila Montasser before we share her presentation. She is a distinguished professor of clinical pathology, chief scientist, chair, stem cell, regenerative medicine, nanotechnology, and tissue engineering research group at the Faculty of Medicine, Manufia University, Egypt. So now we would like to share her slides with us. Anna, would you be able to share the slides, please? Enjoy this presentation. Thank you. And then please put your question at the tab Q&A at the right hand side of the screen. And then as well, you can upvote the most favorable question for you. And then we will ask it at the end of the session, should Leila Montasser be available for us. If not, we will go directly to the next panel. Thank you.
I am Dr. Leila Mahmoud Montasser, Professor of Clinical Pathology, Faculty of Medicine, Manufia University, Egypt. The title of my presentation is Modern Technologies. Where are we living? Chief Scientist, Chair, Stem Cell, Regenerative Medicine, Nanotechnology, and Tissue Engineering, SRNT, Research Group, inaugural holder of the SRNT chair, formerly chair founder leader of Clinical Pathology Department, Faculty of Medicine, Manufia University, Egypt. In 2020 and 2021, I was awarded 19 certificates of appreciation for the achievement of presenting successfully 35 global webinars for outstanding contribution to the commitment to provide continuing education to the international community from my home office amid the lockdown of COVID-19 crisis. The certificates were awarded in appreciation of a high caliber speaker, an eminent university professor, and a globally accredited researcher with major expertise. Manufia University is located in the beautiful city of Shibin el-Koum in the south of the Nile Delta and overlooks one of the many branches of the Great Nile River. The other photos front view, while the lower two photos are back view. Outline. I will start with summary of my presentation, then brevity design of some of my experience in the era of COVID-19, then synopsis draws on some of my deep experience in the domain of regenerative medicine, and lastly, conclusion. Brief summary of my keynote speech at Annual Technology, Industry, People, and Economics 3D Printing Conference Virtual Global Event 2022, January 18th, 20th, titled Modern Technologies. Where are we living? 3D printing is all about cutting out the middleman. This benefit is being carried over to by printing in the laboratory to cut out the middle step growing cells in the lab, in vitro, and just implanting stem cells directly into the body for growth in situ. In situ bioprinting could be used with robotics for some surgical procedures, as it is less patient invasive, with less pain, less recovery time, less chance of infection, and less time spent in the hospital. Anticipating the utilization of mobile printers for emergency cases and in developing countries and distant zones. 3D bioprinting as an additive biomanufacturing technology, having potential to fast-forward translational research, as it had the capability to fabricate artificial tissues and organs that closely mimic biological tissues or organs. As an emerging area of research in the field of tissue engineering, 3D bioprinting has scope in the development of implantable tissues and organs, construction of tissue organ models, and high throughput disease cancer models for pharmaceutical and toxicological studies. Further, this area has diversified with the continuous upgrading of 3D bioprinters and biomaterials, which play major roles in the architectural quality and functionality of bioprinted construction. Addressing these technological complexities requires an integrated approach involving expertise from different areas of science and engineering with lateral thinking. Bioprinting remains a promising solution for addressing the increasing organ shortage for transplantation globally. The ability to generate tissues for transplant with a lower immune response risk holds significant promise in the fabrication of artificial organs. The recent progress in hydrogel science, including the development of dynamic switchable hydrogels and oxygen-producing hydrogels, provides more and more methods that enable control of cell microenvironments. However, the full potential of 3D bioprinting can be realized by improving upon the printing speed, capability to bioprint at various scales, availability of bioprintable materials and hydrogels, vascularization of tissues, innervation of tissues, and on-demand skillful fabrication and cell maturation mechanisms. 3D bioprinting involves printing cells and materials like extracellular matrix components together to form a viable tissue construct following a one-step biofabrication process. This is followed by incubation of the 3D printed tissue or organ in a bioreactor before any further experimental procedures are performed, and then passed on for preclinical and clinical trials. Tissue defects resulting from disease, trauma, or surgical resection require treatment to restore tissue structure and function. There are certain challenges related to reconstructing complex tissue defects, such as those affecting the skeleton or craniomaxillofacial area, and those resulting after surgical debridement. Such effects are difficult to treat using conventional and standard size implants. In particular, they need to be treated by using modified or trimmed implants or constructs. 3D printing offers the possibility to provide constructs that can be pre-designed to precisely fit defect size and shape. These constructs are usually designed and engineered ex vivo and subsequently implanted into the body. However, this process has several challenges related to logistics. 3D printing in a location far from the operating room, sterility, and necessity to modify, trim, adjust, or combine different pieces to fit the shape and size of treated defects. In addition, the size and shape changes and thus 3D printed construct will not always fit following the debridement of defect. Instead, 3D printed implant will be installed on a subsequent second operation, and this two-stage procedure carries higher risks and problems. Ideally, a customized implant should be produced and implanted during the same sitting. However, this approach has been limited by various technical, procedural, and regulatory issues thus far. This ideal solution would employ a commonly used 3D printing technique in the operating room and 3D print constructs in situ. This concept may involve the use of either handheld printers, as in Figure 1, or robotic arms carrying printer nozzles that are controlled by computers and scanners, which constantly measure the exact size of the defect, as in Figure 2 and 3. The integration of developments made in robotics and computer-assisted interventions will also enable achieving more precision in printing procedure. These advances will enable developing more innovative solutions for in situ 3D printing to be employed in operating rooms. When fully deployed, the technology of in situ 3D printing will result in more accurate reconstruction of tissue defects and result in faster and more efficient healing of tissue defects. Briefly, 3D printing starts with modeling, where visual blueprints from computer-aided design. Then the second step is printing, wherever 3D printers read the design and lay down successive layers of materials. And lastly, finishing, with what after printing, the supports are removed or dissolved to get the final product. 3D by printing integrates the conventional 3D printing imaging and cell gel to fabricate functional tissue for regenerative medicine, pharmaceutical, preclinical drug screening, and animal-free meat. Current tissue engineering strategies lack the capability of fabrication of fully functional tissues and recapitulate their heterocellular structure. 3D printing shares the three basic components with the conventional Gutenberg paper printing. the 3D model file to be printed, blueprint, is analogous to the text file. The bioink, which comprises cells and other bioactive materials, is analogous to the ink, and the 3D printer is analogous to the printers that deposit the ink on a substrate or print platform. Bioprinting has a great potential to surpass the traditional tissue engineering techniques and can offer solutions to many existing technological hurdles. Summary of my keynote speech at first International Conference on Digital Transformation, scheduled on the 16th to 17th of September 2021 at Dar es Salaam, Tanzania, titled 3D Printing Technology and Digital Transformation Innovation for Digital Health Sustainable Strategies. The 2030 Agenda for Sustainable Development highlights that the spread of information and communications technology and global interconnectedness has great potential to accelerate human progress, to bridge the digital divide, and to develop knowledge societies. We could commit ourselves to harness the possibility of information and communications technologies to realize the 2030 Agenda for Sustainable Development, understanding that they could fast advance towards the health concerning sustainable development goals. Digital transformation of healthcare can be troublesome. However, now another industrial revolution emerged called Industry 4. Industry 4 is the current trend of automation and data exchange in manufacturing technologies. It includes cyber physical systems, the Internet of Things, and cloud. Summary of my keynote speech presented at 4th International Conference on Biomaterials and Nanomaterials, September 29th, 2021, from Edinburgh, Scotland, titled Emerging 3D Printing Biomaterials in Tissue Engineering. Transplantation medicine is one of the most challenging and complex areas of modern medicine. Before the starting of the transplantation period for organs has been high and has overtaken the ready. So, evolution of novel technicalities in biomedical engineering has aided to promote numerous prospects for modern stents for transplant trials. Synopsis notes on some of my deep experience in the domain of regenerative medicine. Isolation protocol of mesenchymal stem cells on nuclear cell separation from bone marrow on fecal. Primary culture of mononuclear cells, then subculture of isolated mesenchymal stem cells. The cells from primary culture were seeded for first and second passage. Inverted microscope images of morphology of stem cells. A. Rounded adherent cells on the second day after first seeding. B. Fusiform fibroblastoid cells with many rounded cells on the seventh day. C. Fusiform fibroblastoid cells with 50% confluence on the 12th day. D. Increase the fibroblastoid adherent cells on the 15th day with 80% confluence. E. Differentiated mesenchymal stem cells on day 4 with some change in the morphology of mesenchymal stem cells to rounded and the epithelioid cells in between fibroblastoid cells. F. Differentiated mesenchymal stem cells on day 7 with more morphological change of mesenchymal stem cells to polygonal hepatocyte-like cell. The left figure shows electrospinning set. The middle figure shows diagram of electrospinning setup, while the right one shows scanning electron microscope image of a poly-L lactic acid scaffold. This paper, presented at Digital SPI August 2024 online from California, USA, as a video with audio narration titled Innovative Patterning of Electrospinning Fabrication Nanoscaffolds with Cell Culturing for Liver Tissue Engineering. Failure of human body organs is believed to be one of the most important health problems all over the world. Stem cell-based therapy has received attention as a possible alternative to organ transplantation, owing to the ability of stem cells to repopulate and differentiate at the engrafted site. Before transplantation, cells were generally seeded on innovative modality of nanoscaffolds fabricated by electrospinning technique that recapitulate the extracellular matrix and provide cells with information that's important for tissue development. My invited speech at SPI 2016 August from San Diego, California, USA, titled Articular Cartilage Tissue Engineering with Plasma-Rich Growth Factors and Stem Cells with Nanoscaffolds. Conclusion. So far, research into the field of in situ 3D bioprinting has shown visibility and usefulness. This novel research field provides great potential for tissue engineering and regenerative medicine applications, where pre-operative planning of construct size and shape is difficult or impossible to predict. Advances in robotic surgery, fused imaging, and computer-assisted medical interventions should also be integrated to develop future clinical in situ 3D bioprinting process, which can be translated to products for a variety of surgical applications. By the way, about textile applications, 3D printed blouses, suits, jackets, shoes, and dresses. Thank you.